Hello and welcome to Mathematics Scholars. I'm Hansa, and in this video, we will be solving this question of trigonometry, where we are going to prove this result. So let's proceed with the solution. How we are going to solve it? See, the key approach that we are going to use here is, first of all, because we need to prove sum of cot square k pi by 2n plus 1 is equals to something. The idea that we are going to use here is framing an equation whose roots are cot square k pi by 2n plus 1. So if we can find an equation whose roots are cot square k pi by 2n plus 1, where the value of k moves from 1 to 3 until n, then from that equation what we need to find out is just the sum of the roots. So let us see how we can write down that equation. What you have to do whenever you come across an equation where you want to frame an equation having the roots in the form of cot square, you should start with sign. You should start with sign means what we have to do in this situation is look at the denominator that you want in the angle. You want 2n plus 1. So you start with considering sine 2n plus 1 x equals to 0. You just start with sine 2n plus 1 x equals to 0. I'm marking it as 1 and you will come to know why I'm taking sine 2n plus 1 into x equals to 0 as we proceed with the solution. Now what is the next step? The next step says that sine 2n plus 1 into x. Just check whether all these values of k, for all these values of k, that means for k is equals to 1, for k is equals to 2, the angles which are written over here are satisfying equation number 1 or not. So yes, we can verify it very quickly. Just by observation, we can say that all these are actually the roots of equation number 1. Well, I don't want an equation in terms of sine. What I want is an equation in terms of cot, or in fact cot square. So for that, what you have to do is, now you have to take a help from de Moivre's theorem. I'm going to make use of de Moivre's theorem. I'm going to take the help of de Moivre's theorem to rewrite the left-hand side of equation number 1. But how we are going to use it? So for that, let's see. What I'm going to do is, I will write cos x plus iota sin x. What you want in front of x is 2n plus 1. So just raise the index 2n plus 1 here. Now two things. Left hand side I'll be using de Moivre's theorem. But the right hand side I'm going to use binomial theorem. I'll expand it using binomial theorem. So I'm writing the right hand side, which is going to be 2n plus 1 c naught cos power 2n plus 1 x. Then we will have the second term plus 2n plus 1 c1 cos raised to the power 2nx, and then we have iota sin x whole power 1. Let's write on the third term as well. 2n plus 1 c2 cos power 2n minus 1x iota sin x whole square, and keep writing till the last term. Till the last term. The last term is going to be 2n plus 1 c2n plus 1 cos power 0. So let's not write it. Iota sin x whole power 2n plus 1. This is the right hand side. While on the left hand side, when you apply de Moivre's theorem, what we are getting is cos 2n plus 1x plus iota sin 2n plus 1x. What I'm going to do now is I'm going to compare the imaginary part of both the sides. Comparing the imaginary part will definitely give me sin 2n plus 1 into x. So that is what now I'm going to do. On comparing sin 2n plus 1x, or comparing the imaginary parts both the sides, I will get an equation, or you can say a relation, which says that sin 2n plus 1 into x turns out to be 2n plus 1 c1 cos power 2nx multiplied by sin x minus 2n plus 1 c3, only the imaginary part I'm comparing, cos power 2n minus 2 sin power 3x, and so on. till the last term. The last term is definitely going to be involved because iota index we have odd here. So last term will also be involved. So this is sine 2n plus 1 into x, which I am going to make use in equation number 1. So left hand side of equation number 1 I am going to replace sine 2n plus 1 into x with this expansion. So let us go back to the question and proceed with sine 2n plus 1 into x equals to 0. I'm going to replace sine 2n plus 1 into x with the expansion which we have just derived. So it will become 2n plus 1 c1 cos power 2n x into sin x minus 2n plus 1 c3 cos power 2n minus 2 into x sin x. Keep writing. The next term is going to be positive. So we will have 2n plus 1 c5 cos power 2n minus 4 sin power 5x. And here also we have sin cube x and so on till the last term equals to 0. See, we are having in mind that we need to create an equation involving cot square. How can you create cot square? So to create cot square in this expression, you just divide this whole expression with the highest degree of sign available in this equation. So we know because the last term of the expansion will be involved, the highest degree that we have in this equation is 2n plus 1. So I'm going to divide the whole equation, both the sides, by sine raised to the power 2n plus 1 into x. Obviously assuming sin x to be not 0. Sin x is not equals to 0. Okay? Sin x is not equals to 0. Now divide the expression with sine power 2n plus 1 multiplied by x, or sine raised to the power 2n plus 1 into x. Okay, let's see what the equation will now become. The equation will take the form 2n plus 1 c1, and see the first term has converted to cot. It has become cot power 2n x. Similarly, when you divide the second term, you will be getting cot power 2 raised to the cot raised to the power 2 times n minus 1 into x. Let me write down the third term as well. It will become 2n plus 1 c5. Again, it is cot raised to the power 2 times n minus 2 x and so on equals to 0. So here is the equation that we wanted. We are having an equation in terms of cot. But I cannot apply the theory of equations in the trigonometric equation. So I'm going to convert it into polynomial form. And for that, the simple substitution that we are going to make use here is cot square x is equals to y. Cot square x equals to y. Fine. So let us keep cot square x equals to y. We will have 2n plus 1 c1 into y square minus 2n plus 1 c3 multiplied by y raised to the power n minus 1. So the first term also you can see that it's not y square. We are keeping cot square y means it will become y raised to the power n. The third term similarly can be written as 2n plus 1 c5 y raised to the power n minus 2 and so on equals to 0. Well, the equation that we have written is of degree n. And what are the roots of this equation? Obviously, the roots of this equation are going to be in the form of cot square. But cot square what? Cot square those angles which we have assumed as the roots of, or which are actually the roots of equation 1. So we have the roots of equation 1 as k pi upon 2n plus 1. Right? So we have cot square k pi upon 2n plus 1, where k takes the value from 1 to n. So all these are the roots. All these are n roots of the equation that I have just written. What I need to find out in the question? I need to find out the sigma of these values. So that's it. We are going to end the question now. We are going to write down sigma, the sum of roots using the theory of equation portion, where k starts from 1 and goes till n. And we can say that answer turns out to be 2n plus 1 c3 upon 2n plus 1 c1. When you simplify it, your answer reduces to n into 2n minus 1 divided by 3. So see, we have proved this result. This is the answer, or we can say hence proved sigma cot square is equals to right hand side. Now see, although we have proved the question, But we can prove other results also, because it might be possible that the question is framed not just with sigma cot square. Maybe they are framing the question with sigma product of the roots taken 2 at a time. Or we can say that sigma cot square pi by 2n plus 1 multiplied by cot square 2 pi by 2n plus 1. So sum of the roots taken 2 at a time. If you want to calculate this thing, this can easily be calculated again using this equation. So from here now I can write that my answer will turn out to be 2n plus 1 c5 upon 2n plus 1 c1, which can further be simplified whenever required. So I have also calculated that what is going to be sigma cot square into cot square, or sum of the roots taken 2 at a time. And not just this, as we have written the equation, even if they create a question in which sum of the roots taken 3 at a time is required, yes, we will be able to get the answer for that too. Now see, one more thing I would like to share here. What other thing is possible in this question? We have solved the general question, and see the importance of solving the general question. Now, whenever they frame a question, because generally the questions are framed by putting the values of n. We have solved the question for positive integers. So any value of n can be used in the question and a new question can be framed. Like if I keep n is equals to 3, suppose I'm keeping n is equals to 3, then my question will convert to the form, prove that sigma cot square pi by, keeping n is equals to 3, so 7, where the value of k pi by 7, the value of k starts from 1 and goes till 7. So goes till 7, goes till n is 3 here. What is going to be the answer? For the answer, now we are going to write, just replace n by 3. So 3 into 6 minus 1 by 3, and the answer turns out to be 5. So this itself is a very good question. How we can solve it? Yes, we can solve it using the approach that we have used for the general question. Another value, you can see that n is equals to 7 k. Also, we can create some new question. I'm keeping case from 1 to 7. Now we will have cot square k pi by, denominator 15. What should be the answer in this situation? Again, you just need to keep n is equals to 7 over here. So keeping 7 gives me 7 multiplied by 13 divided by 3. So here's the answer, or we can say that we have created a question and got the answer using the general form. Well, that brings to an end to this video. Thanks for watching. Please like the video and subscribe to our channel. Bye-bye for now.